Okay, so we're going to continue talking about complex numbers today. The first thing I was going to do is just to show you some animations of some of the things that I said last time before writing some more stuff on the tablet. So let's see. Okay, so the first thing I said about complex numbers is that if you want, you can think of them as points on the plane, and that's kind of like the most convenient interpretation for us. So they are points, but the reason why you call them complex numbers, that word numbers there is just because basically you can do with them essentially the same things that you would do with regular numbers. So with regular numbers, you can add regular numbers, you can subtract regular numbers, you can multiply regular numbers, you can divide regular numbers, you can take square roots, exponentials, logarithms, etc., etc. And my claim, what I'm going to tell you a little bit about today and next time is that you can basically do the same things with the complex numbers. So you can multiply them, you can add them, you can divide by them, you can take square roots of them, you can take the exponential of them. Like so, all the regular operations that you're accustomed to with numbers, you can more or less like translate or like find an analog for the complex ones. So the usually mathematics, once you take other classes, you'll notice that adding is easier than multiplying as a rule of thumb. Like so, almost by default, you call multiplication whatever ends up being the hardest operation. So like it's not like maybe that much of a coincidence. But so if you have two numbers, which are two complex numbers, again, I can think of them as being represented by points on the plane. So this is like the first point. This is the second point. So this is like the first complex number, the second complex number. And what I mentioned last time is that to add them is kind of like the most, if you had to make a bet, the most straightforward thing you could try maybe, which is like you just add the corresponding entries. So 1 plus 5.41 is 6.41, and 3 plus 1.01 is 4.01. So that's the addition of complex numbers, which has like this nice geometric interpretation. Yes, sorry. Oh, right. You could, yes, like that's one of the ways to do it, like in terms of vectors. Yeah. So if you think about them as kind of like in terms of like an arrow that starts at the origin and terminates at the corresponding point, it corresponds to, yeah, so there are kind of like two ways to interpret the addition. One is that with these two vectors, these two arrows, you can kind of construct a parallelogram as you see here, and then this diagonal corresponds to the sum. The other interpretation is kind of like that you can move one of the vectors so that it begins where the other ends, and then that like this third side would be kind of like the third side of a triangle. But it's not that we're going to kind of like rely too much on this geometric interpretation. It's just that it's nice to know that there is one, whenever you draw the picture, whenever you do the operations. And if you take up three, or if you have taken a physics class, you'll talk about vectors, and you'll see that this is kind of like the usual interpretation for like vector addition. But just to kind of like show you how that looks like. So like, you can kind of like start moving like one of the points or the vectors, and the parallelogram like changes accordingly. And so does like the diagonal. Okay. But it's the important thing is like the addition is done entry by entry. So in that sense, it's easy. Then you move to the multiplication. So when you're multiplying complex numbers, you are not, you don't multiply the corresponding entries. Multiplying the corresponding entries will make the problem kind of like too boring in a sense, because if the only thing that you do is multiply the corresponding entries, then you might as well you're just working with two separate lists of numbers, right? Like the X entries and the Y entries, and you're doing everything without knowing that the other one exists. So kind of like any interesting concept of multiplication will be something that involves all the entries in some weird way. because that way they all become aware of the existence of the other entries. So what I was, and that's kind of what I ended up with in the last few minutes of Monday's class. The way we think about multiplication in terms of complex numbers. So the easiest way is first in terms in a way that's very related to polar coordinates, because if you have two complex numbers, again, you can think about them in terms of like these arrows that you draw from the origin. So the idea is that to multiply them, whatever the multiplication will be, is an arrow, a number, right? An arrow whose length equals the product of the individual lengths. So you multiply the lengths of these vectors or arrows, and the angle is the one that you get by adding together the angles of the individual numbers with respect to the x-axis. So kind of like the way multiplication works is that you multiply the length or the radii, if you think about it, kind of like as a, or multiply the distances. Multiply the distances to the origin of like each individual number, and you add the angles that the numbers make up with the x-axis. So for example, that's kind of what you see here. Like this is like, now maybe this is like 10 degrees. Maybe this would be more like 45 degrees. And then like the sum would be around 50 degrees. But I could do something a bit like, again, I can increase this one. Let's see. You know, maybe now this is 45. And then 45 plus 90, you know, 45 degrees plus 90 degrees, that's 135, which would land somewhere in here, right? So that's why the angle of the new vector results. And the size, it is that the length of this arrow or the length of this number is kind of like the product of the individual lengths. So like just to kind of like, you can make the numbers work out more nicely. You can zoom. So like, for example, if one had like size 2, if one has length 2, which is like on this circle, and the other one has length 1, right? 2 times 1 is 2, right? So like this, like the product would stay on this circle because it has still distance to the origin. Or if you do 2 and 3, so 2 times 3 is 6, right? So now this one has distance 6 to the origin. So the distances, the way the multiplication is defined is so that the distances multiply and the angles add. And it just turns out to be like a very useful operation, and I'll kind of like explain today why it ends up being like a convenient way of defining the multiplication. But this is kind of like the most geometric way to understand the multiplication of what's going on. So, and then you can kind of have fun with it if you want it. So like, you could take like kind of like, you could take a shape on the plane and just imagine like, oh, what if you multiply every point on this shape by a number, and then kind of like the effect is kind of like a rotation and then a stretching factor, which is kind of like fun to play with. But I may tell you more about that like later on. But the idea is like kind of like multiplying in a sense, like rotates and stretches, kind of like the images on the space. Kind of like you can do the same here. Like if you have a triangle, multiplying it by a complex number, what it will do is kind of like rotate it and stretch it. Like you can like make it bigger or shorter depending if the distance is bigger or less than 1. And then this is kind of like the angle of rotation. Okay, so you can have fun like with pictures on the plane just by using complex numbers. It's like a useful way to, you know, like work with images. But you know, like it won't be like the main focus for now, but I just thought it should be useful, like nice to mention it. Okay, let's see. Okay, so as I was saying, let me move this around. Okay. So as I was saying, you have the multiplication. The way it works is you have a complex number, which I'll call Z1, which is X1, Y1. You have another complex number, C2, which is X2, Y2. And then the product, which I'm just going to call Z, which is going to be X comma Y, and my goal will be to find X, Y in a moment from X1, Y1, X2, Y2. You'll see how that works. But again, as I was saying, kind of thinking about it in terms of polar coordinates, if this has like a distance to the origin, which I'm calling R1, and this one has a distance to the origin, which I'm calling R2, then the distance to the origin of the new one is the product of those distances. So it's R1 times R2. And if the first angle was theta1 in polar for the first point, and the second angle was theta2 in polar, then the new angle for this third point would be theta1 plus theta2. So kind of like distances, like the lengths multiply and the distances are added. That's kind of like a summary of like what's going on here. So you add the angles and multiply the lengths. Is that okay? And notice, this movie seemed like an obvious thing to worry about. Like, why would you worry about this? But actually, you do like later on in life. So it doesn't matter in which order you multiply them. C1 times C2 is the same as C2 times C1. So like, oops, notice like, like that. Because again, like this is just multiplying the distances, which it doesn't matter in which order you multiply the distances, that's still the same number. And it is adding the angles, and it doesn't matter in which order you add the angles. 30 plus 60 is the same. 30 degrees plus 60 degrees is the same as 60 degrees plus 30 degrees. So based on how I define things, this product, it always like, you don't have to worry about like the order in which you do it. Which in mathematics, whenever that happens, you say that this is commutative, like if not that it's like a word that you have to worry about, but you say that the product is commutative. But like, again, if you ever have to take other more advanced math classes, you'll see that that not always happens when you define other types of products, commutes. Okay. So that is nice. Like it is nice to have like this geometric picture on how you multiply the complex numbers, but it is useful to have like a more algebraic version for doing this. So the question is, how can you find X and Y from knowing X1, Y1, X2, and Y2? That's also like a useful thing to know. And there like something like interesting happens. So now what I'm going to answer is how to find X, Y in terms of X1, Y1, X2, Y2. Yes.
What you mean, rather than in polar, where it's
Correct.
easier, okay.
Right. Instead, if I were insistent of having like a formula in terms of Cartesian, kind of like a Cartesian formula. This is kind of like the polar version of how to multiply things. But what if you wanted to multiply them Cartesianly? Like, like using Cartesian, like, how, I mean, there should be a formula, like, So like, that's what I'm going to try to show for you. Okay, and it always has, like with many of these things, it always boils down to a right triangle. So the right triangle is like, like the most important triangle of all. So let me draw the right triangle that we need here. So if this is XY, there's a right triangle here. We know that this angle is theta1 plus theta2, right? Because like the sum is the sum of the angle is the sum of the angles. And we know that this hypotenuse, the length of this hypotenuse was the product of the length of the other two like distances or hypotenuses. So this hypotenuse has length R1 times R2. So what does polar say in this case? It says that X is R cosine of theta, right? So this says that X, what is X here? X is R, but what is R in this case? R is this number. So it's X is R1, R2 times cosine of theta, but what is cosine of theta? Theta1 plus theta2. Right, so, and literally this is just polar, right? Like this is how we switch in polar from X to R and theta. R, X is R cosine of theta, if you remember in polar. It's just that here, like R and theta are given in terms of like the individual R's and thetas, right, from before. So I can put like the polar conversion, right? If you had R, you had theta, it is X and Y, and then X is R cosine of theta. Right? It's just that in this case, R happens to be a product of R1 and R2, and theta happens to be theta1 plus theta2. Is that okay? Is that making sense? And there's a reason maybe why you were taught this formula for the cosine of the sum of two angles back in high school or wherever you saw this. So there's this magical trick formula that says that the cosine of theta1 plus theta2, that's just the product of the cosines. So it's cosine of theta1, cosine of theta2, minus the sine of the angles. By the way, you don't need to remember this formula. I'm just like using it once so that you see where it comes from, but I'm not like, don't worry if you don't remember it. But that's kind of like the formula for the, which in the special case where theta1 is the same as theta2, you get that cosine of 2 theta is cosine squared minus sine squared, like which you may remember. Okay, and now we're like, you'll see that this is already kind of like all the information that we need. I'll just distribute first. So I'll write this as R1, R2, cosine of theta1, cosine of theta2, minus R1, R2, sine of theta1, sine of theta2. Okay, so let's see. And now it's just recognizing this in terms of previous stuff. So for example, what is R1 cosine of theta1 is X1, right? Because so what is R1 cosine of theta1? That should be X1. And then what is the other color that I used? Did I use red? Okay. And then let's just keep the colors matching. And then what is R2 cosine of theta2? That's X2. So you get X1, X2. Okay. Minus. And then, okay. R1 sine of theta1, that would be Y1, right? And then R2, oops, and then R2 sine of theta 2, that would be Y2. And then that gives you X entirely in terms of X1, X1, X2, Y1, and Y2, right? And of course, I'll give you a trick to memorize this formula. Like there's like a very elegant way to memorize it, but this solves the problem, right? Like at least for X, like that gives you a complete information about X in terms of the initial coordinates of the 2 points. Okay, so making sense. By the way, I'll mention this in a couple of minutes, but why did you put a plus here? Like someone recognize that as a dot product. So I'll tell you that in a moment. But I mean, like that doesn't make sense right now, but like it would make sense in a couple of others. Okay, and how about y? So what is y? Y would be R1, R2 sine of theta 1 plus theta 2, right? And then you have to remember, okay, what was the formula for the sine of theta 1 plus theta 2? It's kind of like sine with cosine. So it's sine of theta 1 with cosine of theta 2 plus cosine of theta 1 with sine of theta 2. So it kind of like with cosine of the sum is cosine, cosine, sine, sine. The other one is sine, cosine, sine, cosine, sine. So like kind of like combines that sines and cosines. So let me just write it down. So this is sine of theta 1, cosine of theta 2, plus cosine of theta 1, sine of theta 2. Which is why if you put sine of 2 theta, that's how you get 2 sine theta cosine of theta. That's where like it comes from. And so this gives you like R1, R2, sine of theta 1, cosine of theta 2, plus R1, R2, cosine of theta 1, sine of theta 2. And it's kind of like similar to what I just did. What is R1 with sine of theta 1? That is Y1, right? And then what is R2 with cosine of theta 2? That would be X2. And then let's go back here. That would be what is R1 with cosine of theta 1? That would be X1. And what is R R2 sine of theta 2? That would be what? That would be Y2. And then again gives you Y in terms of Y1, X2, X1, and Y2. Is that okay? So far, so good. Is that making sense how I got this? And as I'll say in a couple minutes again, if you somehow had ended up with a minus here, this would give you something that's called a determinant. So I'll explain that later. So like this multiplication like ends up having a bunch of useful properties that you'll see in a moment. Now, of course, like the problem is like how do you memorize these formulas? Because like you also have to be practical. So you want a way to remember how to find these formulas. So I'll give you like a useful trick to memorize these formulas. So, but we just found them. There was no cheating involved when finding them, like it really is what it is, like, so now once you know the right formula, you can cheat to get to, which is not so much of a cheating, but I'm just saying, like, you can use tricks to get to the correct result. So now is how do you memorize this? Okay, so there's a very useful way of rewriting complex numbers, which if you have seen them before, probably that's what you will recognize. So for that, like you just have to have like a clever notation for expressing a complex number. And so the idea is that if you had a complex number, um, kind of like the formula of the sum rule. The sum rule allows me to break this into two pieces. You'll see which two pieces. So we'll write this as x comma 0, which is here. And I'll write this plus um, plus 0 comma y, which is here. That is what the sum rule allows you to do, right? Because if you notice, like, what is x plus 0? That's x, right? What is 0 plus y? That's y. So this is fine. And that's why I'm drawing the picture so that you see also that this would work nicely. Because if you add this, if you think about it in terms of the parallelogram that I said, like, it just happens to be a rectangle in this case. And this side is just like one of the diagonals of that rectangle, if you were to draw the parallelogram. So I can draw it again if you want it, if you want to see it. And then you say, okay, kind of the reason for doing it, this splitting, which is called like a linear combination, by the way. One of the reasons for doing this splitting is that now here, the only variable that shows up is x, so you can kind of like take it out. So you can say, okay, this is the same as x times 1 comma 0. Why? Because, x times 1 like would be x and x times 0 would be 0. And then this would be y times 0, 1. Because like in the sense that y times 0 is 0 and y times 1 is 1. Y times 1 is 1, yeah. And I believe I mentioned this before. This 0.01 has a special name in complex numbers. It's called I. So this is baptized I. So this is the number I. So this is called I. And kind of like the convention is like, okay, you don't write 1, 0 explicitly, so you just write it as x. Or think about it as 1. So this kind of represents the number 1 that you know of, know and care about. So like this is 1. So you get x1 plus y times I. And so you get, no one explicitly writes 1, so you just get x plus y I. So usually kind of like the normal way, or well, I mean, I guess like you write it no, I think it's b times a. It's fine, like to write it this way. I mean, like whether you put the I first, like it doesn't matter too much, but I just write it x plus y I. So usually the traditional way of expressing like a complex number, say like, for example, if this had been like the point 3 comma 5, you would say that this is 3 plus 5i. Or if this had been like the point, what could this be? This could be like maybe let's say that this is 4 and this is -2. If this is 4 comma -2, then this would be 4 minus 2i. So sometimes when people explain complex numbers, they just say, oh, complex number is a plus x plus yi, and then, like start from there, but it does kind of like, makes it a little bit more mysterious what's going on. Uh, But like from our perspective, this is just like a very clever way of rewriting things so that it looks kind of like more streamlined notation.
Why do you define 0 1 as I or like square root of -1?
Oh, well, the thing is like, I'll kind of like, you see it from like the rule for multiplication is that if you call this I, because of the way I define the multiplication, it has the property that I times I equals -1. Yeah, and the thing is like again, if someone saw this very passing video, historically, like people just like introduce this I, and they just introduce like talk with square root. Like for example, like imagine like you wanted to solve x squared plus 4 equals 0, right? If you try to solve it, you would say like x squared equals -4, and in a traditional math class, you stop there, right? But if you just kind of go along with it, you say, well, maybe x plus or minus the root of -4, okay? And then if you take out the 4, that is plus or minus 2 times the root of -1, right? If you just go with it. And then, like for, again, historical reasons, like people had to do this, and they just called this I. But it was until decades or almost centuries later that they thought about it in this perspective, which kind of like dissolves some of the mystery in surrounding all this stuff. But yeah, like at the beginning, like they would just like say, "Oh, I just like a number that's correct -1." That's why were called imaginary, because they were not convinced that such a thing would exist. It's just that it would allow you to finish doing certain calculations that otherwise you could have done before. Yeah. This, for now, I'm just declaring that I want to call this I. It's going to be related to this I, because with this formula for multiplication, we can check that I times I gives you -1. So that's why it's related to this. But for now, it just happens to be like a clever way to refer to 0, 1, right? But the reason why it's referred that way is because it doesn't match this. It does have this magical property that the number I is supposed to have.
Just like a coincidence that the x and y variables were related and not products of evidence.
Oh, no, it will be not a coincidence, but I still, before making it more clear, like, you have to talk about the conjugate of a complex number, which I'll do in a moment, but, no, everything is related. Everything, like, not sound very new age, but everything is connected, like, yeah, so, like, yeah, especially in complex numbers, like, everything just complex numbers, like, if you ever take a math class, is wherever you dreamed in mathematics happens, like, all the properties just are super nice, like, not that we're going to do this, but for example, in complex numbers, the moment a function has one derivative, it automatically has infinitely many derivatives. Like crazy stuff like just starts happening like out of thin air. Like, it is like they do have a lot of like properties like work very well together. And so like, it's really like, very magical like stuff, like, like it is very nice. So like mathematics, because everything is kind of like as good as it can get. So like compared to complex numbers, everything will always fail in some way or another. Complex number has like all the properties that you could ask for in life. So, but okay, why am I introducing this notation? Because it gives you like the best way to memorize the product formula. So with this notation, you can just find the product by foiling or distributing. So, but before that, okay, maybe I should mention that I does square to -1. Okay. So I called I 0, 1. Okay. So what is I in the picture? In our picture, I is right here. This is I. So I think I did mention this briefly last time, but based on this, what would be I squared if you think about it from the polar perspective? What would be I squared? in this picture? Well, what is the angle that this number should have? 90 plus 90, right? Pi over 2 plus pi over 2. So whatever this is, its angle should be 90, like pi over 2 plus pi over 2, right? Which would be 180, or like, I mean, pi radians, right? So it's like, its angle should be 180, so it should be on this side of the x-axis, and its distance, right, what it should be, its length. This has length 1. I mean, it's pretty easy to see. So 1 times 1 is 1, right? So its length should be 1 times 1, which is 1. But we do know what that is, right? If you have something of length 1, right? 180 degrees of length 1, that should be the point -1 comma 0. So I squared is the point -1 comma 0. I'm sorry, -1 comma 0. Oh yeah, let's. But because of like this funny way of writing the points that I just mentioned a bit earlier, you can just write this as -1 plus 0i, and like no one would write 0i explicitly, so you just write it like -1. So that's how you end almost like with miraculously that I squared equals -1. Which again, historically, that's kind of like how it started, And again, it wasn't too much later that people came up with this like representation in terms of like the complex, in terms of the like RXY plane, which makes it a lot more transparent, but like. Okay, and now that we know that I squares to -1, I can give you the clever way of doing the product. So this is the clever way of finding the formula for the product. So clever way to multiply complex numbers. So like again, if I wanted to multiply C1 times C2, right, where C1 is X1, Y1, and C2 is X2, Y2, right? What you can do now is kind of like rewrite these numbers in their like I version. So you can say that this is the same as X1 plus Y1I times X2 plus Y2I. And then kind of like, I'll just distribute. So I'll do the first with the first, so it's X1, X2. Then I'll do the first with the second, so that would be X1, Y2I. Then I'll do the second with the first, which will give me Y1, X2I. And then I'll do the second with the second, which will give me Y1, Y2I, right? And then, okay, so how does this simplify? So what is I squared? We already talked about that. That's -1. So let's group these two terms together because they don't have I at all. So I'll group them together. You get X1, X2 minus Y1, Y2, right? And then let's group the stuff that has the I together. And you get X1, Y2 plus Y1, X2. And if you go back, I mean, if we could go back for a second, x1, x2 minus y1, y2. That is precisely what I said x would be. X1, x2 minus y1, y2, right? It's right here. And the other one was x1, y2, y1, x2. X1, y2, y1, x2. So it reproduces the entries for that we had just found. So it recovers like the previous formula. So what I'm saying is that you don't have to memorize the formula. You just have to memorize that you can distribute basically when you do product. So these are the formulas for, so this was like the formula for X from before, and this was the formula for Y from before. Yes,
Because of the two eyes.
correct. The two I square into -1. Yes. Yeah, exactly. That's why I. So just maybe to do a numerical example, like, in practice, how you would do it, like if you were computing things with like actual numbers, like then you would like, like, so if I told you, okay, like this is usually how things would be written. Like, so for example, if I say C1 is 2 minus 3i, and C2 is like maybe 1 plus I, right? Then I could ask you what is C1 times C1 times C2, and the idea is that you distribute. So what is 2 minus 3i times 1 plus I, and again, when you FOIL or distribute, you get 2 plus 2i minus 3i minus 3i squared, right? And like, well, let's just go baby steps. So 2i minus 3i would be -i, and then I squared squares to -1, so minus minus becomes a plus, so you get plus 3. And so that would be 5 minus I. Okay, so by the way, as a terminology, not some extra terminology is that Um, if you have a complex number, and you write it as x plus y times I, x is called the real part of the number. So this is called the real part. So this sometimes is called written RE of C for real. And then the other one is called the imaginary part. So this is called the imaginary part. Imaginary part. So sometimes it is called like M of Z for imaginary. So the number in front of I is called the imaginary part, then like the number that's along or in front of one. Like, one is secretly always there. So this is always x times one, So the number in front of one, which is just like the number, is like the real. Yeah.
Have had an imaginary sort
Yeah, no, you could always, if you had wanted to, you could always have thought about, yes, like X being the real part and Y being the imaginary part. Yes, yes. The thing is, like, until now, it that's kind of like wouldn't have been the beneficial. Like, what makes this useful is the multiplication kind of like intertwines everything. So because if you look at that's kind of like it takes some time to kind of like stare at it and realize it. But what this is saying is that the product involves the knowledge of all the four coordinates together, and this other product involves all the four coordinates. So you have to be aware when you multiply complex numbers, everyone has to be aware of all their neighbors. You know what I mean? Because here's like a bad definition. Like, so if you have that, if you take this is 3, 5, and this is 4, 2, I'll just multiply them by multiplying their entries, right? So you can get 12 and 10, right? This would have been a bad definition because then the first coordinates only need to be aware of their existence and the second coordinates only need to be aware of the existence of the other. But the first one wouldn't care about what the second one is doing. So it's like a non-interaction formula because like it is completely separate from one another. So like that's why it's not like an interesting formula because you might as well just work on an Excel spreadsheet, which you call, with the columns all being independent of one another. Like what kind of like ties the topic together is the fact that you have to be aware of what everyone else is doing in order to compute like the formula. Right. So if you are stuck in a world where you only have to add things, like talking about complex numbers doesn't really give you anything interesting. Like you might as well say, oh, let's just add two list of numbers. It's only the multiplication that binds things together. Like if someone who's taking around, right, the same thing. If you learn how to add matrices, like the way to add matrices entry by entry. That's not interesting. I mean, that's okay, but it's not interesting per se. What's interesting about the matrix multiplication is that you have to do all these operations to find like a single entry of the new template. In a similar way, which what happens in complex multiplication. The fact that you are kind of putting everyone to talk to one another makes like the topic interesting because otherwise, like you might as well just work with separate lists of numbers. Okay, so that is, as I was saying, like the x coordinate is called the real part, the y coordinate is called the imaginary part. There's another useful notion which is called the conjugate of a complex number, which is just like a reflection with respect to the x-axis. So let me kind of like mention this one. So another useful operation is called the conjugate, and I'll show you how it looks like in a picture. So the idea is that if you have a complex number like this, at an angle theta. Let's call this angle theta. The conjugate is basically what you get if you imagine like putting like a mirror along the x-axis and just looking at the reflection that you get with respect to this mirror. So the conjugate is a mirror image with respect to the x-axis, or like a reflection, if you want. It's like the conjugate is called z bar. So this like it's just like a horizontal line above the number z. And what it corresponds to is like, like there are two ways to think about it. In terms of a point, it's just x comma negative y, right? Because you're just changing the sign of the y coordinate. Like the x coordinate remains the same because like again, the mirror is along the x-axis. So you only flip the y coordinate. So if it had been negative, right? If it had been negative, the conjugate would have been positive. Like positive becomes negative or negative becomes positive for like the y coordinate. So that's one way to think about it. The other way to think about it, like from this polar perspective, is that the distance to the origin is the same, right? Like they have the same distance. So if this is r, for the conjugate, the r is the same, right? But what is the angle? So the angle, there are two ways to think about the angle. One is to just say that the angle would be 2 pi minus theta, right? Because if you notice, like if you kind of measure, like how should I put it? Oops, sorry. Like if you measure like this angle with respect to the x-axis, like you almost get to 360 degrees, but you just have to subtract the angle theta. But no one like really does it that way because it's better just to write it as this angle of negative theta if you just understand that a negative angle means counterclockwise. So usually, like now I will put kind of like an arrow to the angle to just like remind you that the angles are measured counterclockwise. So another way of writing this is as negative theta, but then you think of this angle moving. Like a negative angle, you just think about it as being in the clockwise sense. And this looks a lot nicer. Like, in practice. So if you say like an angle of negative 30 degrees, that just means 30 degrees like going down, clockwise. And that work. So this is kind of like how like time on a clock works, right? What is like, I don't know, 11 hours plus 3 hours, like, that's like 11 plus 3 is 14, but with respect to the clock is just 2, right? Because like what are 3 hours after 11 a.m. like it's 2 p.m., right? Like you just go back to where you started. So every time you get to 360 degrees, it's kind of like you restart the clock, at 0. So okay, that makes sense. So why is oh, yes.
So the angle two by minus theta, is that the angle like?
With respect to
The.
counterclockwise. 2 pi minus theta would be if you measure things counterclockwise. But I'm just saying like it looks kind of messy to write it that way. So you can just say that it's the same as saying that so I'll put here like that this is if you regard the angle clockwise, right? And this is if you had measured it counterclockwise, right? Clockwise. But if you notice in the picture, like do it counterclockwise. So, but if you look at the picture, right, like going 320 degrees this way is the same as going 40 degrees that way, right? Like, so it does correspond to the same angle. It's just like in practice, it's kind of like messy to write every single time 2 pi minus theta. But you would just write the angle negative. Why would you do the conjugate? First, something that is important to notice is that the conjugate of the conjugate, right? If you look at the mirror image and you take the mirror image back again, you get to where you started. So the conjugate of the conjugate returns you to where you start. So that just gives you Z. That looks a little bit messy, because let me try to put like the arrows, like the lines like a bit more like separated. Like the mirror of the mirror is yourself, like You're the mirror image of your mirror image. That's like one way to think about it. So mirror of the mirror is the same thing. It's the same object. Is that okay? And then the other thing that's useful, the reason why the conjugate is useful is because it has like a nice property when you multiply a number times its conjugate. So what is a number times its conjugate? Well, I mean, we can kind of see it here, right? We can like you can do it two ways. You can do it like kind of like I prefer to whenever we're multiplying things, it's always nice to do it geometrically to see what happens. So what should be the angle of z times z bar? 0, right? Like that's what we're doing. So if angle 0 means that it should be along the x-axis, right? It should be angle 0, so it's along the x-axis. And what is the length? The length is the product of the length. So it just squares the length of the vector, right? So if you kind of like, and you can also check using the formula in terms of x and y, that z bar is just going to be x squared plus y squared comma 0, or like, like because this is going to be r squared. So the way to write this in like the usual notation is that it's x squared plus y squared. So that is the distance squared. Like the nice thing about the conjugate is that the z times z bar is the distance squared of the point to the origin. That makes sense. So yeah.
So for all fronts, like normal. Okay.
Opposed to what you were speaking about on the art data plane or something like that, or like
I feel like usually I see complex numbers and like them like an I or something.
well, I mean, okay. What you're thinking, maybe there are two things that may be going on there. One thing that could happen, which we're not going to get too much into it. That for example, like for example, if I write something like y equals x squared, right, as a function, right, when it's a function of one variable, right, then the graph is in two dimensions.
Yeah.
But if I write something like w equals f of z, like z squared, right? Because this kind of like depends on two variables, this is going to depend on two variables, but the graph is four-dimensional. So for like, then like the graph cannot be drawn on the same plane as the original one, so you have to do kind of like a plane for the values for the domain and another plane for the codomain. And then, so that is one possible thing you have seen before, where like a graph of a function of complex variables requires four axes. Like kind of, yeah. And so you can call, but if you just had like, if you were saying that one is just called like the imagine, like there's nothing that you would call per se like the imaginary plane. You might call it like the imaginary axis, which would be this y coordinate. But yeah, for graphs of functions of complex numbers, then you do need 4 dimensions, and you cannot see the graph in,
Sure.
yeah. So like that would be like, so usually one way to do that is kind of like to draw like 2 copies of the plane, one kind of for the domain, the other one for like the range or like the code. And you kind of like see where the points get mapped to. But this, that is what you would do in like an actual complex analysis class, like or complex variables class, which we're not doing. We're just doing like the very basics, of it.
Yeah.
So,
Yeah, can you go by R squared is 0?
um, like y r squared.
Yeah.
Oh, but this is not 0, right? No, no, so what I'm saying is that, right, if you think about it from the polar perspective, what should be the angle for this product? Like this was theta and this was negative theta, right? So they add up to 0. That just tells you that the vector or the number is along the x-axis, right? And the length of that number or that vector should be the product of the length, right? R squared, but because it's on the x-axis, like that means that the y coordinate has to be 0. The y coordinate, but the x coordinate is like x squared plus y squared. Oh, because it had like this kind of has to be the entire length of the number. Right, like so the length of this, actually I could write it this way. Like, so what I'm trying to say is that this number, like maybe to kind of put like an intermediate step, this number should have been r squared comma 0, because if it is on the x-axis, so y has to be 0, right? And its distance to the origin has to be r squared. So there's no other place for like the entire, like the entire distance has to be contained in the first entry. But then r squared by Pythagoras theorem just happens to be x squared plus y squared. So that is where like that comes from. Is that making more sense? Yeah, it is a little bit tricky, but here's the thing. This is why it's useful to have 2 different ways of multiplying things around, because then you can just do it algebraically if you feel more comfortable with it. So if I ask you what is z times z bar, right? That is x plus y times I times x minus y times I. And this is actually a difference of square formulas, if you think about it. This is like a plus b times a minus b. So it works exactly the same way. So it would give you x squared minus b squared, but b squared in this case is y times I. And because I squared squares to -1, that makes it a plus. So like that's the magic of like I, that like kind of like you turn negative numbers into positive numbers, like the I squared kind of like would if there's square, like makes squares negative, which is kind of like weird, like this. But yeah, like this is kind of like, it is like a more algebraic way of understanding the same formula, and depending on your perspective, at least it's always more direct to find it this way, but it doesn't have necessarily the same meaning geometrically as like if you actually think about, oh, okay, what are the angles? What are the lengths that you get? Like, this gives you a little bit more perspective, into what's going on. Oh, I'm just saying that like what this, so when I wrote this, I just mean like this number represent I mean like I just meant it in the sense that then this number literally represents like the distance of like, because if this was xy, right? This was xy. So you had a point xy and its distance squared to the origin was r squared. But that is essentially what z times z bar is. So I'm just saying that like this number z times z bar is coincides with the distance squared to the origin of the point that you started with. Is that making sense? Okay, and so why would you do this? Like, so like I'm saying that like this is like a useful thing to do. So one way, maybe I'll finish with this today, and then next time I'll explain to you the last topic about complex numbers that we'll talk about, which is like Euler's formula, which is like a very surprising result, which you might have seen before. All kind of like just like kind of like maybe the craziest formula in mathematics that e to the pi I plus one equals zero, whatever all of this means. So I kind of explain like kind of where that comes from next time. But at least to kind of finish like in a more like concrete place today. Why is z bar like this conjugate useful? Because that allows you to find the reciprocal of a number. So as I was saying, with numbers, you want to add, subtract, multiply, and divide. So I still haven't told you really how you would do a division, like, so z bar comes to the rescue to divide, Um, so why is C bar useful? Because allows you to find the reciprocal of a number or the reciprocal of a number, a countless number. So by reciprocal, I mean what you would usually call like z to the negative one, which in a more familiar notation you would write as 1 over z, right? And then, okay, and then it's kind of like where like, whenever you're defining something new, it's where like there's some creativity involved because you have to think, okay, what is the appropriate way to define this? And then you are like, okay, whatever this is, right? We still don't know what this means. I still don't know what it is. But whatever it means, hopefully it would have the property that you can multiply and divide by a number and still the same fraction, right? Like that's kind of like a nice thing about fractions. If you have a fraction, like I left by what do if you have like a fraction like 1 over a, that's the same as 1 over a times b over b, right? Like you can always rescale a fraction and that should be fine. So if you just go with that, like based on that, like I'll kind of like, this should work or like you will define it so that this works. So kind of like in this case, you will like that 1 over z should be the same as 1 over z times z bar divided by c bar. I mean, like again, that's kind of like uh be like a crazy thing to ask. But let's think about it in terms of like the actual coordinates that this would have. This would have like coordinates x comma negative y, right? And we already talked about this, or like I can write it in the I notation. Like this is the same as x minus y times I, right? So like, again, just to do the picture, maybe this is x plus iy or y times I, right? And what would this be? So the top becomes x minus y times I, and what is the bottom is z times z bar. But what was z times z bar? Is x squared plus y squared, right? that make sense? And if you were to draw this, right? Okay, so what is the effect of drawing this? So x minus yi, that's kind of like the usual reflection, but you're putting this number in the denominator, so it kind of like shrinks the number, right, by this amount. Like because like this is like a number, right? Like this could be 3 or 4 or 5 or whatever the number ends up being. So it kind of like shrinks the vector or like the number. So the way this thing will look like is going to be kind of like in the same direction as the reflection, x minus yi, but kind of like a little bit smaller. And if you multiply these two numbers together, these two numbers together, it's like an easy check that you get one. Like you can do it algebraically, but basically the idea is like the reason why that works is that if this had length r, the way this is built is so that it comes up having length 1 over r. So the lengths multiply, so 1 over r times 1 over r gives you 1, and the angles are still like opposite of one another, so it gives you back to 0. So this is what I'm calling z to the -1. So you can do like just check by multiplying that z times z inverse gives you 1. So the trick about the z bar, the reason why z bar is useful is that it allows you to invert a number. Let me maybe do a great example just to grab this so that sorry.
So why were we able to multiply the divide by C4 in the first place if we still weren't exactly sure?
Oh no, it's kind of like n justified the mean. I'm not sure, but this formula is unambiguous. This formula is unambiguous, so I'll just take that. I had to do something shady to get here, but you drop the shady part and then you just say, oh, this is the formula. Like you don't care where it came from. I mean, of course you do if you were trying to define things, but you can there's nothing wrong with this definition, because this is like a real number, right? We do know how to divide a real number by a real number. Like that's the magic. We do know how to take a fraction of a real number. You just take the individual fractions. Like you're doing x divided by x squared plus y squared, which is fine, and you're doing y divided by x squared plus y squared, which is totally fine. So kind of like the trick was to kind of rewrite things so that you don't see the complex number at the bottom. That's kind of like where the magic happened. But yeah, like I didn't know if I could do that. I just went along with it, and then it kind of like worked. Yeah. But let me show you how it would look in practice. So for example, this won't take too much time, but I do want to show you something more concrete. So imagine I ask you to simplify like, let's say 2 minus I divided by 1 plus I. So if you again, like the way I'm thinking about this notation is that this is 2 minus I times 1 over 1 plus I. Right? Like that's how fractions would work. That's what you mean by a fraction. And then to this one, I applied the magic trick. The magic trick is multiply and divide by its conjugate. Okay. And again, the conjugate, the only thing that does is change the sign of the imaginary part. So it was +1, so it becomes -1. Is that okay? So far, so good. Everyone with me? And now everything can be done because 2 minus I times 1 minus I can FOIL, right? I will be able to FOIL the top. And 1 plus I times 1 minus I is just like the difference of square formulas, right? Or like it's essentially Pythagoras theorem, but it would be like, like I can just write it like this. The bottom will always give you a real number. That's the point. A regular number. So, and then you would get, this is 2 minus 2I minus I plus I squared. And then like this would give you 1 squared minus I squared if you write it as a difference of squares. minus I squared. And so that gives you what? It gives you 2 minus 3I minus 1 divided by 1 plus 1, right? Because I squared is -1 and minus minus becomes a plus. So that would give you what? It gives you 1 minus 3I divided by 2. And that's perfectly fine because you can kind of like what you don't want is to see the I at the bottom. That's kind of like the idea. You want to move out things around so the I appears always at the top. And by doing the conjugate tree, you get every time you have a fraction of complex numbers, you can always multiply by the conjugate of the denominator, and then you're good. You know, you have a and this like maybe just to wrap this up, this kind of like justifies the claim that you can multiply numbers, you can divide by numbers, complex numbers. I mean, add complex numbers and subtract complex numbers. So it gets as close as you would like to like what should be called like a regular number. Because again, for those who have seen like, for example, other things like matrices, in general, you cannot divide by a matrix. Like a closest thing of division by matrix is like an inverse of a matrix, which requires like a condition on the determinant. Like, and that's only for square matrices. So I mean, this is like a lot better, like, you know. Yeah.
So I just wanted to ask, like, what does this mean geometrically? Like, if we see both those complex numbers just like points on the plate, so what does the dividing?
Oh, right. Like maybe I'll, for those who are interested, they can stay and I'll tell you. But what is Z1 divided by Z2? Basically, this would be a number, right? Whose length is the ratio of the lengths of the numerator. So it's a ratio R1 divided by R2, and the angle between like of this new number is the angle of the first one minus the angle of the second one. That will become more clear once I write Euler's formula, because then it's really easy to see that. So the angle here is like θ1 minus θ2, basically. So you take the ratio of the lengths, and then you subtract the angles. So it's kind of like a difference of angles. You know, like the angle between the two numbers. It is what you people would call, I'm not like, you know, everyone, like, you know, the angle between vectors, you know, like if you thought about this, like in the numerator as a vector and the denominator as a vector, it would be the angle between the vectors. So, and then you ratio the length. Okay, so yeah, there's only one topic left. We just go over like this Euler's formula, which I'll explain on Monday. And that's kind of like the last topic for the exam. I'll probably send you like a study guide for the final, like by tomorrow. So don't forget that we'll have like these extra office hours on Wednesday in person for 4 hours. So you can also show up to those. I also have my online office hours on Tuesday, but it's usually easier just to go through things in person. So you can stay there because it's like a regular classroom. So you can stay there, work for like the 4 hours if you like on problems. And if whenever something comes up, you can just like ask me. But let's end here and we're almost done with everything. Okay. So